All right, let's just jump right in. Today, we're tackling a mission that honestly sounds like it's straight out of a spy movie. We're going to install a really powerful security system, IBM SOAR. But here's the kicker. We're doing it in an environment that has zero, and I mean zero, internet access. Our job here is to take what looks like a super dense technical manual and turn it into a clear step-by-step strategy. This is how you win in the ultimate digital lockdown. So here's how we're going to break this down. Our whole operation has 5 main stages. First, we've got to understand the battlefield itself. What exactly is an air gap? Then we'll prep our supply drop, which is all the software we need. After that, we cross the digital divide, build the system inside the secure vault, and then, and this is crucial, we'll run through some final checks to avoid the most common traps. Let's get into it. Okay, section 1. What is an air gap? Look, before we can even think about installing anything, we have to get our heads around the battlefield. An air gap isn't just a feature or a setting. It's the entire world we're operating in. And believe me, it changes all the rules. So what is it? An air-gapped environment is exactly what it sounds like. There is a physical gap of air between it and any outside network. No Wi-Fi, no network cables leading to the outside world, nothing. Think of it like a submarine's computer system. It's totally self-contained. Now, why would anyone do this? Well, for critical infrastructure, governments, or big financial institutions, this level of isolation is the absolute best defense against hackers. For us, though, it's our single biggest obstacle. And this slide really just lays it all out. It's a night and day difference. On the left, with a normal internet connection, your computer just reaches out and grabs whatever it needs from the cloud. Easy. But on the right, in our air-gapped world, it's a whole different ballgame. It's like building a ship in a bottle. Every single piece, every component, every dependency has to be gathered by hand, packaged up and carried in. It's a completely different logistical challenge. So that brings us to section 2, preparing your supply drop. Since we can't download a single thing inside that secure zone, we have to get everything ready beforehand. All of this prep work happens on a normal, everyday computer that is connected to the internet. This is where we build our entire installation kit from scratch. The process is really methodical. You have to follow the steps. First, we set up what's called a private Docker registry. Just think of this as our own private warehouse where we're going to store all our software. Second, we go out and download every single container image that SOAR needs. Third, and this is key, we relabel all those images so they point to our new private warehouse address. And finally, we package it all up, the whole shebang, ready for the big move. And boom, here's the command that kicks it all off. This little script, docker local registry up.sh, is what actually builds that private warehouse we've been talking about. It creates a secure, local home right on our prep machine that's going to hold every software component we need to pull this off. And this slide shows you exactly what I mean by relabeling. We use a command called docker tag, and it's basically like slapping a new shipping label on a package. See, the original address points to a public server, QIO. We're changing that address to point to our private one, k3sregistry.duckdns.org. Why? So that when the system is inside the vault and needs some software, it knows to look right there in our local warehouse, not out on the internet. All right, our supply drop is packed, it's labeled, and it's ready to go. Welcome to section 3, crossing the digital divide. Now we get to the really tricky part of the mission, actually moving all of these assets into that secure, completely isolated zone. So what's actually in this package we're moving? Well, it's a lot more than just the app. We've got the core operating system components, called K3s. We've got all the SOAR application images we just retagged. We're even bringing the entire data set for our private software warehouse. And critically, we have the SSL certificates. Think of these as digital passports. Plus all the scripts we'll need to put it all together. We made it. We're inside the vault. All of our assets have crossed the divide. Now for section 4, the real work begins. This is where we assemble and configure the entire system in a world with no Google, no downloads, no outside help at all. And this brings us to the central question, right? We've brought all the software in with us, but the system itself is designed to look for things out on the internet. So how in the world do we make it look in our local warehouse instead? The answer is actually pretty clever, and it's all in this one little configuration file, registries.yaml. You can think of this file as the system's new address book. We're basically telling it, hey, anytime you see a request for software from that public website, q.io, I want you to redirect that request and look for it here in our local private warehouse. It's a simple little text file, but it's a powerful redirect that makes this whole thing possible.
Okay, so we've solved the location problem, but that immediately creates a new one. In a closed network with no way to check with public authorities, how do the different parts of our system prove who they are and trust each other? How do they establish secure connections?
The answer is those SSL certificates we brought with us, our digital passports. Every piece of our system, like our private warehouse, has to present its passport to prove its identity. Now, normally, these passports are verified by a big, trusted public authority on the internet. Since we don't have that, we have to become our own passport authority. We have to create and approve these digital IDs ourselves. So, how do we actually do that? It's basically a three-step process. First, we use a tool to bundle all the passport information into one secure file. Second, we use another tool to import that bundle into the system's key store, which is just its official list of trusted IDs. And finally, we just restart the main services. That forces them to load the new rules and recognize our newly trusted components. We are so close. The system's built, it's configured, and all the parts trust each other. We're on the home stretch now. But let me tell you, this is exactly where tiny little mistakes can cause catastrophic failures. So let's talk about the final checks and the most common traps. And here it is, the two words that will strike fear into the heart of anyone doing an air-gapped install: error image pull. This is, without a doubt, the most common, most frustrating error you will ever see. It just means the system tried to start up, but it couldn't find the software it needed. So when you see this error, you know your internal supply chain is broken somewhere. The only question is, where? It's time to put on our detective hats and start following the clues. And here's the good news. The clue is almost always right there in the logs. You run a command to describe the problem, and it will tell you, plain as day. You'll see the error, image pull, and right after it, the reason. In this case, the image was not found. The system looked for it in our private warehouse exactly as told, but it just wasn't there with that exact name. This gives us a really clear troubleshooting checklist. You just start asking the questions. First, are the image tags exactly right? A missing version number is a classic mistake. Second, did I make a typo in the address book, the registries.yaml file? Third, is the passport system working? Can the components actually trust each other? And finally, you check the absolute basics. Can the computer even connect to the private warehouse over the network? And what's the number one single most common cause of this error after all that work? A simple typo, a misspelled name in the configuration file, or a forgotten version tag on an image. It's kind of wild. Despite all this insane complexity, success or failure often comes down to just being meticulous and double-checking your work. And once all the software is running and the errors are gone, we execute this final command. This is what officially links the two main parts of the system together. It's the final handshake. And with that, mission accomplished. So we did it. The system is installed, it's running, and it's secure inside its digital vault. But success just reveals the next mission. In a world where new security threats pop up every single day, how are you going to update and patch the system over time without ever breaking that critical air gap? Now that is the next challenge.